we're working on and take a color or contour and begin tracing. This process will be the same as if you were using a wide field fluorescent microscope or a wide field fluorescent microscope with a structural illumination device. After the tracing of the region of interest is finished, we get the next step to select the regions that we wish to collect images from. Now, we're going to switch from the digital camera to imaging with the laser to capture the images, and you'll be able to see that the scaling has changed to match what we see in the digital camera.
Right, you can see that the camera investigator has recognized, first of all, that you have a confocal, second of all, asks if you want to use it, and then when you say yes, it automatically selects the lens scaling that's appropriate for that device.
Right, and this level of integration that we feel makes this a much more streamlined process than what you were able to achieve in the past in the context of confocal stereology. Here we're setting up our stereological parameters as the X, Y, Z and Y components of our dissector, as well as to indicate the systematic random sampling grid distribution. From step 8, we will be setting our guard zone heights, our probe heights, as well as our mounted thickness height. The mounted thickness height can be obtained empirically. Again, hitting the live camera button, we've already previously selected that we wanted to use the laser from the control. And now we're going to focus up and down, and my favorite process, and I'm sure many of you do this as well, is to focus up above the tissue until you're completely out of focus, and then come down until something is in focus. We'll call this the top of the tissue. We'll then focus down all the way through the tissue, past the bottom, and focus up until we can start to begin to see things be in focus. We will call this the bottom of the tissue, and the difference between the two, the mounted thickness.
Yep, and anybody who's done stereology before knows that what you cut the section at and what it shrinks to by the time you're done with your histological processing are rarely the same.
Correct. So, after we have set up our stereological parameters, the next step allows us to save our images and allows us to name both our images and our DAT files.
This is important because it's going to automatically assign a name to each of those image sets that we're going to acquire.
Step 10 is one of the few places where the workflow differs from a conventional wide field fluorescence for structural illumination, is at the top of the section is set in a combination of Stereo Investigator and Zen. So we set the top of the section, we'll navigate in feed through Zen, and when we're set, our latest at the top, we will hit the resume button on the NDF background. We'll then move the page to the next location.
Via Stereo Investigator.
Set the top of the tissue section in Zen, and then press the resume button in the NDF confocal link macro to set that top.
Yep, so you're just going to toggle back and forth, but the best part is that Stereo Investigator and Zen know when they're each supposed to play a role, so it's seamless.
And so the data from Zen that you just dictated by setting the top of the tissue gets ported into Stereo Investigator, and a topographical map is generated. We can then save all the configuration settings that we've generated in Stereo Investigator for future use. Here, we're ready to begin imaging, and we press the Start Acquire button. And what you can see is if we go back and forth, if we go to Zen, you can see that Zen is now driving the LSM hardware to generate our image stacks.
And it's operating unattended at this point. So what it's going to do is it's going to move to each XY location specified by Stereo Investigator. Stereo Investigator will tell the stage to move to those locations. Then when we get to that location, or when the stage gets to that location, we'll automatically navigate through the section thickness to acquire the desired image stacks that you want, whether it's the entire mounted thickness, just the probe height, or a combination of probe height, guard zone, and images above and below.
Correct. And so what you're seeing now are the two pieces of software, as you mentioned, interacting. Stereo Investigator driving the position of the stage in X and Y, and then the Zen software driving all of the functionality of the laser scanning microscope.
So this is the point where you could leave the scope to continue to work and acquire these image stacks all by itself. You don't have to be here for this process. And in fact, what we're demonstrating now is relatively short. We only did one section, but Stereo Investigator allows you to specify capture of multiple sections and assign them all to the right locations for you if they're all located on the same physical glass slide. And so you can really set this up to acquire bilaterally 12 to 15 sections if you want.
Right. Once you get your imaging parameters established and the rest of the hardware set up, it's really a simple process to get through. So here we see that Ben is finishing up, I believe, the last image stack.
And once it's done,
once it's done, we go back to Stereo Investigator. Stereo Investigator knows that our run is completed. It's automatically saved. And then we get done.
Okay, so what do you do once you've let your event console run all night collecting hundreds of image stacks and naming them for you and putting them in a space where you can get them later?
Right.
We're going to take you through the process real briefly of now. And the option is, the next thing to do is to count those image stacks. And there's a couple of different ways you can do it. You could use your LSM system, the computer that is connected to your LSM to do those counts, or you can take them offline to a workstation so that you can use your LSM for other imaging that needs to be done. You would load the data file into Stereo Investigator, and we select the optimal fractionator workflow because in this case we're going to be counting objects. The data file that we collected with the SLS image stack acquire workflow contains a number of features that are critical in order to be able to analyze the data. We have the stereological parameters that we use during acquisition. We know the location of where each of those image stacks are in S, Y, and Z, as well as across which section they appear in. And we also know the image scaling for those images so that we're going to display them properly. Next, we're going to mark the object. For the optical fractionator workflow, if you count it live, you know that there are 12 steps in that workflow. When you run the optical fractionator workflow off of an SRS image stack acquired data file, you only have 5 steps now. And the full step really that you're going to be spending all your time on is marking the object. Because we have image stacks, we're able to view the stack in 3D with the counting frame overlaid the image stack. That allows you to double check any questionable features that you may wonder about. Is that on the line? Is it in the guide zone? Is it in the guide sector? Now you can load that image stack, see where it intersects with the counting frame, and make an informed decision.
And you could not do this if you were counting it live.
That's correct. That's correct. So that's one advantage of counting with an SRS data file. Finally, like all Stereo Investigator probes, you can view and export the results. Stereo Investigator calculates your estimates for you automatically. It also will calculate the coefficients of errors for those probes and allows you to export them directly to Excel. This streamlines that entire process to make the process of marking your cells to analyzing your data in Excel streamlined and very quick. We provide all the equations that we use to calculate the data so that you can know where we are coming from. So let's see this in action. So I'm going to switch to Stereo Investigator now. So place a reference point, and under the probes menu, I'm now going to set the optical fractionator workflow. I'll select load separate data from an existing file and browse to where that location is. I'm going to open the data file. And you can see that this is a data file of the hippocampus. The dentate gyrus is outlined in pink here, and the striatum radiatum is outlined here in blue. You can see that we've bounced all the way down to step 4, which is the count object step. Because we already know where we're going to sample, and we've already acquired those image stacks at that location, we're ready to count. So we'll select the acquired stacks and hit start. I'll select an object for marking. now, when I look out here, let me zoom in a little bit. So let me tell you what we're looking at actually before I get too deep into this. So this is an image series of tissue that was stained with GLUR1 for the glutamate receptor and Z-glut for vesicular glutamate. Vesicular glutamate is in green and GLUR1 is in red. And so these image stacks were fired at 100x with a zoom level of 5. And so we're looking at very tiny objects here, obviously.
And as we mentioned before, all of that scaling information is shared between the two pieces of software seamlessly.
And so now the process of counting is the same as if you were counting something very large, like somas. You're going to move down through the image stack using the page up or page down key. And when you enter the dissector, you can see that the counting frame now becomes green and red, and we would mark objects as they appear. For example, I can also show you this in 3D. So we can pop the stack into 3D.
So this is what you mentioned before. This 3D tool allows you to make decisions about whether or not an object is inside the counting frame or not, depending on this 3D view, and maybe I can see it easier in this way.
Yeah, so it's just an added tool for your arsenal for trying to decide whether or not some of these objects that may be on the edge, whether or not they should be counted.
Right.
So, for example, if you were looking at this synaptic element and you wanted to say, alright, does it come into focus when it touches the exclusion line or not? Let's move through Z and see whether or not that is the case. And so we're out of the dissector right now, and we can see that it is there. So as we move down, we wouldn't mark that object. So it's just an additional tool to allow you to make these decisions more rapidly and with greater confidence.
Right.
So we would just proceed through the image stack as necessary, marking all of these synaptic elements that meet the criteria to be counted, not just on this stack, but for the remaining stacks on this section and the remaining sections in that animal. Once that's completed, the data is available for analysis and export.
In summary, thin optical sections from confocal microscopes provide the resolution to perform stereology on very small objects, or very small objects that are densely packed, like cord-labeled nuclei, synapses, spines, etc. The tight integration between Stereo Investigator and Zeiss Zen is an enabling technology that greatly simplifies rigorous quantification with confocal microscopy. Automation of image collection and offline analysis offers unparalleled efficiency, and one of our customers has told us that it has made her work 10 times faster, which is exactly what we want to hear.
Absolutely. I mean, think about just the ability to automatically name the successive image stacks across the successive sections that you're going to be analyzing. That's hundreds of sections, saving you the time and the tedium of filling that information out.
And that seems like such a small process, just naming things, but it's a critical aspect of being able to do this that you don't even think about how tedious it can be.
Right, and that's the simplest thing that this innovation does.